Alright, so let's try to solve another question. 865, smallest subtree with all deepest nodes. It's exactly the same question as 1123, lowest common ancestor of deepest leaves. This 865, I think the example looks slightly nicer. You got a picture. This one you don't have that. So I'm gonna talk through this question using this question number, but they are exactly the same question. If you just copy the code here and paste it into the other question, you should be able to get it accepted. Probably only need to change function name or really tiny little tweaks. So let's read the question here. Given a binary tree with the root node as the input to the function, the depth of each node is the shortest distance to the root. So the depth is the number of edges you have to hop to get to that node from the root. So let's say that the 7 and 4, they have depths 1, 2, 3, and this level here, the nodes 6, 2, 0, 8, they all have depths of 2, and this direct children towards this root node here, 1 and 5, they have depths 1. They are the direct children, so there's only one link connecting the node to the root. So that's the definition of depths. And here is the definition of a deepest node. A node is deepest if it has the largest depths possible among all the nodes in this entire tree. So if you're doing level-wise traversal BFS, the very last levels, all the nodes in that level is the deepest node. And then is the definition of a subtree. A subtree is the node and plus all the descendants of that node. It's basically just picking that node and treat it like the root node. And if you treat that node as root node, all the children towards all the children of that node, all the descendants of that node, and the node itself, basically it's a subtree. And we need to return the node with the largest depths such that it contains all the deepest node in the subtree. So the example here we have 7 and 4. These two nodes are the deepest one, and they are connected to 2 here. So this node is the required nodes. If we just think about the second piece of the requirements, it contains all the deepest node in the subtree. Then we have a lot of other nodes that satisfy that, like node 5 and node 3. But node 5 is depth is 1, node 2 is 2. And node 3 here is have depth 0. So the deepest one is the node 2 here. So let's look at if we just draw another node here, maybe like a tang or something that is left child or right child towards node 6, then the answer for this question would change to 5, because if 5 is the root node, is the node that with the deepest depths that's containing this addition node and the 7 and 4. Even though that 3 here, the root node, contains all the deepest node, of course, because it's a root node, it contains everything as its descendants. But the depth of root node 5 is actually larger than 3, so we will return that if that's the case, if we do an addition here. So basically, if we do BFS search to grab all this deepest leaves, deepest nodes first, and then we just backtracking to find the parents of that node, and then because we have 2 nodes here, we keep doing that parent finding kind of strategy until we find just one node there that the parent for the previous levels of nodes that's being backward traversal from the deepest leaves. Then the single node alone will be the node that we want. So yeah, so the strategy is just from top to down at bottom to grab all the deepest nodes there, and for all those deepest nodes, we're just backward searching for a common ancestor, just one single node. So in order to do this backward search, we need to keep track of the parent for every node so that we have a way to go back. So that's pretty much the strategy. We're going to do BFS search first, and along the way we're going to populate a hash map from the node to its parent. So once we reach the final level here, we will do the backtracking, backup, and from bottom up to iteratively replace the nodes with the parent, do that level by level, and once we reach the final state that there is only one node that we obtain through this process, then that node is the node that we want. So that's pretty much the strategy. Let's code it up. Alright, so give myself a little bit of space. So we're gonna have, since we're doing BFS, we're gonna have a queue here. So the first thing we do is level-wise traversal to get to the bottom there. So this is a for loop to iterate over all the, make sure that we pop out all the nodes that we want. And then we just populating this hash map with the trojans be the key and the apparent be the value, so that we can do backward search again later on. So if we have if the node has a left child, we note down the parent and child relationship. And we push the child onto the queue so that in the next level traversal we will visit that. We do the same thing for the right children. Actually, I'm gonna do a loop here. Since there is really nothing special about left and right, we're just gonna do that for both of them. The process is the same, so we doing a little bit of consolidation of the logic here. So then we're done with one level here. Because another thing we need to do is once we reach the last level, there's nothing going to be appended to the queue anymore, so we have to somehow make a copy of the queue to each level. So just do a copy of it. So after this while loop terminated, the last level here contains all the deepest nodes in this tree. And we have also successfully populated this annotation, like a relationship between child node to the parent. So then we're gonna do the backup looking. I'm just gonna call it nodes, I guess. So the angle is to reach a state that we have only one node in there as the parent for the descendants. For this, we're gonna for every node in here, we're gonna replace the node by the parent. And we're gonna use a set to do some deduplication. So let's put the parent node for node in nodes. And then in the very end, we just return the only thing here. Can the input be null? The number of nodes in the tree will be between 1 and 500. So if it's 1, it just have one single node here. The queue is just that node. So this node here should be able to return that node. Yeah, so I think it looks okay. Let's see, does it work on the example? Okay, so so I need to convert this to list, or can I just pop it off? I think so. Right? Yeah, I can. I think I can just pop it. Okay, so let's see if it passes all the test cases. In terms of time and space complexity, yes, I need to talk about that. For time, we are doing pretty much from top to bottom, and in the worst case, if for if we have all the nodes that's fully populated, or almost fully populated on the last level here, not really all the nodes. Let's say that we have a node from here and node from right, in terms of the left descendants and right descendants for the root node. Like we have a 7 here, but if we move the 4 to 0 here, so it's only 2 nodes here, but the parent is the node that we should return is the root node, actually. So if we just move 4 to stick it to as a child to either 0 or 8, meaning that each branch of the root node has a node. The time complexity is actually just from top to bottom and from bottom to top, so it's 2 pass. So it's 2 multiplied by number of nodes in this tree. So it's but the 2 is constant. So yeah, it's 2 pass from top to bottom, bottom to top. And for space, we maintain a hash map between the child to its parent. So it's order of n there. How many nodes now do you have? You have to keep track of how many pairs of parent to child relationship. So that's the timeline space analysis. So let's see if it works. Yeah. Okay, that's a quick question today.